In Chapter 14 of A Student's Guide to the Great Physics texts, we began by talking about the hydrostatic paradox, which is shown in the top row of this figure over here. And the hydrostatic paradox, you'll probably remember, was that no matter what the size or shape of a container filled with water, as long as the hole in the bottom has the same size, and as long as the depth of the water is the same, it will take the same force to plug the bottom. So as I've been promising, Pascal's principle is going to give us a way of understanding why this is true. So why does that hydrostatic paradox hold? So here I'm going to finally explain clearly why this happens. So let's suppose that we have a narrow chamber on the on the left-hand side here, and there's a little hole in the bottom, and this little hole has a plug, and then we have another chamber that is a very wide chamber, like this, and on the bottom we have the exact same size hole, and there's a plug in it also. And let's suppose that we fill both of these chambers with water to the same height. And what I want to demonstrate now is that provided these are filled to the exact same height, the force that's required to plug the bottom is going to be the same in both cases. In other words, there will be a force pushing down here on the left-hand side, I'll call this force 1 prime, and a force pushing down on the right-hand side, I'll call this force 2 prime, and I want to demonstrate that these two forces are the same, that F1 prime equals F2 prime. In other words, if I were to try to overcome this force, and if I were to overcome this force, that is maybe to balance those two forces, I suppose would be better to say, then I would need to use the exact same force. So how is this? So can we demonstrate that this is true? Okay, so in order to do this, let me draw a few more lines here. So let's suppose that the cross-sectional area of this one is A, and likewise the cross-sectional area of this one is A. But the diameter of this one, this larger tube, we'll call that, the area of that one is A2, and the area of this one is A1. And how I want to do this is I want to imagine, let me draw another line right here that's a suggestive line, right there, and also right here. And I want you to imagine that this and this are openings into a chamber full of fluid just below them. So this right here can be thought of as a little fluid-filled chamber, and this right here can be thought of a fluid-filled chamber. And this chamber on the left has an opening at the bottom with area A1, and an opening at the top with, an area A, and the opening on the top of area A1. And this fluid-filled chamber right here has an opening at the top with area A2 and an opening at the bottom with area A. And what I want to do is I want to demonstrate, I want to find out what the ratio F1 prime to F2 prime is. So what is that ratio? Well, on the left-hand side, all of this fluid above is pushing down on this opening with, I'll call that force F1. And all this fluid up here is pushing down on that opening with a force F2. Okay, so let's first consider the left-hand side here. Well, the left-hand side, if we think of this right here, this region, as being a fluid-filled chamber with two openings, then this obeys Pascal's principle. In other words, F1 prime over A is equal to F1 over A1. That is, this force divided by that area is equal to this force divided by that area. And likewise, for the right chamber, if we think of this as a little fluid-filled chamber with two openings of area A and A2, then F2 prime is to A in the same ratio as F2 is to A2. Okay? Now, let's go up to here. What I really want to do is find F1 prime to F2 prime. So F1 prime to F2 prime is, well, F1 prime, let's use this formula right here. F1 prime is going to be F1 times A over A1. And for F2 prime, I can use F2 times A over A2. Okay. Now, what is F1 prime to F2 prime? Well, the A's cancel out, and I'm left with F1 over A1 and F2 over A2. In other words, the ratio of these two forces is the same as the ratio of F1 to A1 over F2 to A2. Well, what is the ratio of F1 to A1? Well, we know that this whole volume of fluid up here is what's causing that force, that weight. So F1 prime is to F2 prime. What is this force right here? It's going to be the mass of all that fluid, mass 1 times g. And what's this force right here? It's all the fluid above it, m2 g over a2. And the g's cancel out. What's the mass of all this fluid right here? It's going to be the density times the area 1 times this height of this fluid right here. So maybe I should put that in right there. We'll call this height h. It's the same height on this side and this side. So area 1 times h divided by area 1. And what's the mass of all this fluid in there? It is density times A2 times height over A2. So F2 prime is to F1 prime. Well, we can cancel out the densities, cancel out the heights, and we have A1 over A1 and A2 over A2, so we're left with 1 over 1, or in other words, F2 prime is F1 prime. So what we've just demonstrated, using Pascal's principle, is that as long as the fluid height is the same, and as long as the area of the holes in the bottom is the same, then the forces exerted on these two pistons will be the same. And that's exactly what Pascal was demonstrating over here. It doesn't matter what the shape of the chamber is. All that matters is if the hole is the same size and the height is the same, then it's going to take the exact same force to plug each. In the very next lecture, which will be my last one on this chapter, I want to focus on some of these diagrams here at the bottom of the page.